Again, everybody, Mr. Kolakowski here. This lesson is going to be about the speed of waves in strings. You could imagine if you pluck a guitar string, if a hammer hits a piano string, when you press a key, what it does is it sends a wave through that particular medium. And there's a bunch of physics that we can learn by studying events like this. So let me start with a little bit of information and then go into a sample problem for you guys. This is from chapter 16.3, and let's jump right into a couple of things that I think are foundational to the lesson. The first thing I want to um, bring to your attention is that the speed of waves through strings. You could take a jump rope, flick your wrist, and you'll see the wave propagate through that particular jump rope, right? Um, it depends on the tension in the string, okay? The other thing that makes a big difference for the speed of the wave through that rope or guitar string, whatever it is you're looking at, is it also depends on the mass per unit length of the string. Okay. Um, in other words, you could kind of call it, to use the verbiage of the textbook here, um, the linear density of the string. That's the correct words I'm looking for. Okay, so that's linear density of the string. Let's take a look at the equation. Okay, so the speed of the wave in the string is going to be equal to the square root of the tension force in the string measured in newtons divided by the mass per unit length of the string measured in kilograms per meter. Let me go ahead and write that out. So F represents, in this context, the tension in the string. It's a force, so it's measured in newtons. And mu here represents, in this context, the mass per unit length of the string. So I'll just write that out here, mass, linear density of the string, mass per unit length of the string. Still getting used to this awkward angle here for writing. Okay, so anyway, mu is m over L. The units on this would be kilograms per meter. And you can imagine if you have a skinny string or a fat string, think of a musical instrument like a piano or violin or guitar. Some strings are skinnier than others, some strings are fatter than others, and that's going to, of course, affect the way in which a wave will travel through the string. All right, let's get into a sample problem, and I think that'll kind of be a good way to show you what this equation can do for us. Okay, so let's imagine we have a wall here. Let's say you have a string. Let me put a pulley system here with a 2 kilogram mass hanging. Okay, so this might be a pulley. This could be a table or something. Okay, and we need to know a little bit about the string itself. The ultimate goal of this problem is to find out the speed of a pulse on the string. So maybe you pluck it here, okay, and a wave propagates. This is a terrible picture, but the wave propagates through the string, and we want to know what is the speed of a pulse on this string. Okay, so let's write down a few things we know about the string. So let's say the length of the string is measured to be 3 meters. Okay, that's equal sign. And let's say that the mass, so you take the string itself and you put it on a scale, and the mass of the string is, I'll just write the mass of the string, is 0.3 kilograms. Okay, so again, I'll write the question over here. What is speed of a pulse on the string? On this string. Okay. Well, we have to kind of look at the scenario. This isn't a guitar where you have a peg that you can turn to create tension. We have this weight on this pulley. Again, this is supposed to be like a pulley system here. This is a table. Okay, this is a wall. And the tension in the string is created by this weight. We can imagine a free body diagram would look something like this, where we have the weight, the tension force, okay? And the tension force that's going to happen on the string over here is the same as the tension force that you're going to have over here, okay? So if we can find the weight, knowing that this thing, this mass is in equilibrium, the weight here, which would be mg, we can go ahead and 2 kilograms times 10 meters per second, that's going to be 20 newtons, right? That means we know that the tension force is going to be 20 newtons. This weight is going to be stationary. When you pluck the string, you're not going to make the mass over here, lower or raise in a significant way. It's going to be in equilibrium, okay? All right, so let's do a little bit of calculation here. We have F is 20 newtons. Okay, so that's where we have that over here. Let's go ahead and figure out the linear density of the string. So that's M over L. That's going to be 0.3 kilograms divided by 3 meters of length of string. So that would be all the string. Basically, it's kind of like a density. It's a linear density here. That's going to be 0.1 kilograms per meter. And if we plug into our new equation, let's see, get a little bit more room over here. Let's see, we're going to do something like this. We're going to take our 20 newtons, we're going to divide by the 0.1 kilograms per meter. Again, I apologize for the sloppy handwriting here. And when you plug that into your calculator, you get 14.1 meters per second. Okay. If the string was skinnier or fatter, that would affect this mu value. In turn, would affect the speed of the wave pulse. On the other side of the story, if instead of, let's say, 2 kilograms here, you had 5 kilograms here. So you had 50 newtons of weight pulling on the string. The tension force would jump up to 50 newtons. You can see over here, that too would affect the pulse and the speed under which it travels across the string. So lots of different things to consider, and hopefully if you read section chapter 16.3 and kind of go through the samples there, you'll be in a great spot to understand how this equation works. All right, thanks for watching, everybody. Talk to you again soon.